Good morning and welcome to a snow day presentation of the review for exam 2. Let me start out with a quick summary of the main concepts and skills that we're looking for, and then we'll go on to some problems. First of all, just a reference comparing the different kinds of functions we've analyzed so far. We have both functions defined explicitly, like a simple curve, a line, y equals f of x. We've worked with that when we try to find or describe level curves. Explicit, we've also seen things like find the line of intersection between two planes. So you find your x, your y, and your z all in terms of a common t. An implicit form of a 1D curve we've seen is the definition of a level set, right? Where we set a two-dimensional surface equal to a constant height, so a constant three-dimensional component, that can be solved for y to make it explicit, or can be left implicit, like when you have circles of certain radius. So that's where level sets come. Going to 2D surfaces, we have our traditional surface, z equals a function of x and y. If we find a level set of that surface, it brings us down to a 1D curve, an implicit version of that 1D curve. If we go on to a 3D hypersurface, we won't worry about the notation for that, but whenever we have a function with more than two inputs, that's the hypersurface. Either we're trying to optimize with it, or we're trying to think about its derivatives, its partial derivatives. When we find its level set, we are actually creating a surface. So if we think of extending something like a sphere to spheres that are growing at a certain radius, then that would be hypersurface. And then at a certain instance, we would have a sphere of a certain specific radius. We can solve for that level set. We could draw that. No, we're not really going to draw that, but it is an example you can think about. What's interesting about it is it gives us a way to represent a surface implicitly and tie it to a snapshot of a higher dimensional object. Now, one example in particular, we've seen this, is with planes. Planes are implicitly defined surfaces. There's an example right down here. We have x, y, z dotted with a normal vector equal to the initial point vectorized, origin to itself, dotted with a normal vector. That is an implicit definition of a surface. It's written in the form of f of x, y, and z equal to some constant, some number. So the idea of a level set always brings us down a dimension. It kind of projects down onto a lower dimension. With these ideas, we can look at gradients and other forms of the derivative. The gradient of a three-dimensional surface is like a level curve set down a dimension. So the gradient of a two-dimensional surface is only graphed in 2D, even though the surface lives in 3D. It's underneath it. And then we can define a slope in a certain direction by dotting this gradient with a specific unit vector. And the vectors that maximize the slope are the gradient direction, or minus the gradient direction. So max positive slope, max negative slope, or min. And then we have the direction of the level sets, which are the directions of zero slope. And they are the directions that dot to zero with the gradient. We just swap the two components and negate one of them. There's two of those. So there's the gradient of a two-dimensional surface living in 3D. We can also construct a gradient of a three-dimensional surface living in 4D by taking the gradient of that function. Yeah, we can think of this f as a capital F. You want to differentiate them. And we take a gradient to our three-dimensional gradient. What we're getting are all the vectors that are normal to this surface. So as a plane, it's just one vector, normal. But if it's something like a sphere is an implicitly defined surface. The gradient of the implicit form of that sphere tells you the direction that's normal at every single point on that sphere, every single point. So that's the main difference. The gradient is always perpendicular to the level set, but if the level set is two-dimensional, that gradient is living in 2D x and y plane. If the function is defined implicitly, that gradient is living in 3 dimensions and is poking outside of the surface. So, 2 main ways of thinking about surfaces, whether we're defining them explicitly and then reduced down to a gradient, or we define them as a part of a higher dimensional output and then bring them down with level set. Our gradients can tell us 2 different kinds of information. What's happening underneath, which direction we want to follow to get the greatest slope on that surface, or what's the direction that's pointing out of the surface. What's the normal direction? And we'll use this normal form more in chapter 14. So we'll use this two-dimensional form a lot now because we're talking about gradients below a curve, trying to maximize, find where your curve and your constraint function line up. So some of the other skills that we'll be looking for is first looking at equations for planes. We need a point, we need a normal vector, we construct that implicit surface for the plane. Looking at sketching level curves. We won't be sketching level surfaces, those are a little bit tricky. Taking partial derivatives, forming the gradient, forming the directional derivative, and applying the chain rule. And the chain rule applies whenever you have nested functions, and you draw that tree diagram for them. And then finding critical points and classifying them with second derivative tests. That's where we set the gradient equal to 0 or each partial equal to 0. And then finding max and min of a function on the boundary. It can either be a function of 3 variables or 2 variables. But what we're doing is setting the gradient of f equal to a multiple of the gradient of g, and that is Lagrange multipliers. Okay, so that's the quick snapshot of the overall topics, concepts, and skills. Let's go and do some problems.